Hello everyone. Today we are going to be looking at flow as it pertains to the extracranial arteries. I have chosen to focus on laminar flow and turbulent flow in normal vessels and also vessels with stenosis present. Here we are looking at normal laminar flow within the common carotid artery. The laminar flow shows consistent color flow through the vessel because all flow is in line with each other. Remember to take velocity samples in the center of the vessel because with laminar flow, the blood in the center of the vessel is moving the fastest due to less resistance. You can also see normal systolic and diastolic wave patterns since the common carotid artery feeds the external and internal carotid arteries. It must display a combination of high and low resistance. Here is an example of normal turbulent flow in the bifurcation due to the large common carotid artery splitting into the smaller internal carotid artery and external carotid artery. The turbulent flow visualized at bifurcations is the reason why it is a common location for stenosis. I also wanted to point out the different flow patterns in the extracranial vessels. If you look at the waveforms for the ICA and the subclavian, you can see they are vastly different. The ICA feeds a low resistance vascular bed, which must be constantly fed, and this is shown with constant flow during diastole. The subclavian feeds a high resistance vascular bed, which does not require constant blood supply, so there is reverse flow seen during early diastole. Another important aspect to note is the high velocity in the subclavian due to the close proximity to the heart. In the image, you can see properties of the Reynolds number law. The Reynolds number is equal to velocity times fluid density times 2 times radius divided by viscosity. As we learned in lesson 2, turbulence can develop more readily in larger vessels with high flow. The Reynolds number increases as velocity increases and viscosity decreases. So in a clinical application, this would make sense when we are told stenosis in the subclavian is more common on the left. The higher velocity increases the Reynolds number, thus increasing the likelihood of turbulent flow and the buildup of plaque. Now we will be looking at flow in tortuous vessels and in vessels with stenosis. Turbulent flow is shown when the machine assigns a color for flow moving toward or away from the transducer. This shows the different directions of flow within the vessel due to resistance along the vessel wall, and it also shows a difference in flow patterns in the center since the vessel is very tortuous. When flow moves around a curve, there is a difference in flow speed from the inner edge to the outer edge. So this difference in speeds causes more turbulent flow. For an example, think of a river that twists and turns a lot. Another example is in the presence of stenosis. As you can see on the image I obtained from radiopedia.org, there are many different flow patterns and colors happening. It starts with the laminar flow in the distal common carotid artery, and as you get to the bulb, it shows aliasing, meaning higher velocities. Then there is a mixture of flow patterns within the stenosis or narrowing, and as you get more distal to the stenosis, you can see the flow starting to return to laminar. When looking at the spectral Doppler, we notice velocities within the stenosis are over 400 centimeters per second. And this makes sense because, as we already discussed, the Reynolds number and velocity are directly related. This high velocity due to present stenosis is increasing turbulent flow patterns. We also know from flow characteristics of a stenosis in lesson 3 that upon the exit of a stenosis, turbulent flow is present, and distal to a stenosis, there is a lessening of velocity. This allows the return of laminar flow. I hope you enjoyed this presentation and it helped to solidify your understanding of flow patterns within the extracranial arteries. Thank you.